Hello everyone, welcome back to the lecture series on magnetism in condensed matter physics. In the previous video we have talked about the Weiss's theory, which assumed that there exists a local magnetic field known as molecular field, which is proportional to the magnetization of the material and which is responsible for the alignment of spins in ferromagnetic materials. And we have seen the case when there is no external magnetic field and still there was some spontaneous magnetization. Now let's see what is the effect of an external magnetic field. So first of all, let me give you the equation we derived it in the last lecture. In the previous video, we have seen that the ratio of spontaneous magnetization with the saturation magnetization was equal to the Brillouin function, where y was equal to g mu b j times b plus lambda m divided by kVt. And the saturation magnetization is given by n g j mu b. We had also calculated the Curie temperature by equating the slopes of Brillouin function and the another linear function, which gives Tc equal to g mu b j plus 1 lambda times ms divided by 3 kb. And rearranging this will give you the saturation magnetization as 3 kb Tc divided by g mu b times j plus 1 times lambda. Now, using the expression for Curie temperature and equation 2, we can find the ratio of Yn Tc as the further simplification will give you now assume the case when there is no external field which corresponds to the spontaneous magnetization state, and let us consider the value of J is half. Then Y divided by Tc will be equal to 3 by 2 times lambda m divided by 3 by 2 times lambda times T times the saturation magnetization. And the simplification will give you the value of Y as the ratio of spontaneous magnetization with saturation magnetization divided by the ratio of temperature with the Curie temperature. So therefore, the ratio of spontaneous magnetization with saturation magnetization is equal to the Brillouin function, and which was 10 hyperbolic function of y for quantum spins with j equal to half. So therefore, using equation 6, we will get the ratio of spontaneous magnetization and saturation magnetization as 10 hyperbolic of m divided by ms whole divided by t divided by tc. So this represents the phase transition equation. Now let us try to plot this equation 7. If you assume the ratio of m and ms is y and the ratio of t and tc is x, then you can see the functional variation of this equation 7 is 10 hyperbolic of y divided by x. And if you plot this equation, you will get something like this, where at x equal to 0, there is maximum value of m divided by ms, and it drops to 0 when the t by tc ratio is equal to 1. Here there also exists another solution which is trivial. So this represents the phase transition for the absence of magnetic field. Here in the first region there is ferromagnetic phase, while when the temperature is greater than Tc, there is paramagnetic phase. Next we will see the case when there is an external magnetic field. So let's apply a magnetic field for j equal to half. So in that case our y will be equal to b plus lambda m divided by lambda times t by tc times the saturation magnetization. We can split it in two terms so that in the absence of magnetic field, this y will correspond to the previous equation. Now again, the ratio of spontaneous magnetization with saturation magnetization was Brillouin function, and which is equal to the tan hyperbolic function for j equal to half. So let's put the value of y here, and you will get this. Now for ferromagnets, lambda times ms is very greater than 1. So let's define a quantity which is reciprocal of it, which will be very small than 1. And assume that y is equal to m divided by ms and x is equal to t divided by tc. So in that case, this equation will reduce to y is equal to tan hyperbolic of y plus a1b divided by x, where you must remember that this a1 is very small than 1. Now you can plot this particular equation in any of the plotting software, and you will get the curve as like this, where you will see that there is a tail appearing here and the phase transition is disappeared. And if you increase the magnetic field, the curve will shift upwards from the x-axis. So therefore, the application of magnetic field kills the phase transition. Now there exists an interesting question that how to measure the Curie temperature in real systems. It is because the real samples consist of many domains, and without an applied field, these domains orient randomly. So therefore, at b equal to 0, you don't see a sharp curve like this, but instead you will see that there is no net spontaneous magnetization. So therefore, you need to apply a small magnetic field so that you will get a curve like this. This small external field biases the system toward one orientation, thus breaking the symmetry and revealing the ferromagnetic order. But the question arises here that we don't know where is the location of the Curie temperature from this curve, because there is no sharp transition there. So therefore, in that situation, we take the derivative of above curve. If you see in the above curve, that you will see that above and below the TC, the slope is almost constant, while at the transition, the slope is abruptly changing. So you will see a sharp peak or a dip at the transition, and this dip corresponds to the Curie temperature. Also, if you plot this equation as a function of magnetic field, you will get a curve like this, which mimics a cube root function. So therefore, you will see that y is proportional to b raised to power 1 by 3. Now as y was proportional to lambda m plus b, and since lambda m is very larger than external magnetic field, therefore y will be proportional to the magnetization. So this curve represents the magnetization as a function of magnetic field, and you will see that magnetization is almost proportional to b raised to power 1 by 3, and this approximation is valid at the transition temperature. And this variation you can see here in this phase transition curve also, that as you increase magnetic field, the spontaneous magnetization increases with b as b raised to power 1 by 3. Now let's try to see this phase transition from another point of view, where we will also derive the equation for Curie-Weiss law. Now let us apply a small magnetic field B for temperature greater than the Curie temperature, so that the value of y will be very low, and the Brillouin function can be approximated as j plus 1y divided by 3j. So therefore, m divided by ms will be equal to, and the simplification will give, also if you remember, we have defined it Tc as g mu b j plus 1 lambda ms divided by 3kb. So therefore equation 1 can be written in terms of Curie temperature as, and the rearranging will give. Now the susceptibility is given by limit b tending to 0 mu naught m divided by b, so which will be equal to, and the simplification will give the susceptibility equal to mu naught Tc divided by lambda times T minus Tc. So therefore the susceptibility is proportional to 1 over T minus Tc for temperatures greater than the Curie temperature. This is known as the Curie-Weiss law. So if you plot the susceptibility of ferromagnetic material as a function of temperature, you will get a curve like this. So if you check here that this is the susceptibility of ferromagnetic material in the paramagnetic region. So but you may ask that what is the susceptibility value in the ferromagnetic region? And why did we choose only the temperature range greater than the Curie temperatures, not less than the Curie temperatures? So the answer is that below Curie temperatures, the susceptibility is very high, and it is not well described by the Curie-Weiss law. It is because that the ferromagnetic materials exhibit spontaneous magnetization, and the magnetic domains are aligned even without an external field. So the susceptibility is effectively huge and nonlinear, and at the Curie temperature, theoretically the susceptibility approaches to infinite. It is because at this phase transition the domain alignment breaks down and the susceptibility peaks sharply. But above Curie temperature, the susceptibility follows the Curie-Weiss law, and the material becomes paramagnetic, and the magnetic dipoles are disordered but can align with an external field. So therefore the susceptibility decreases with increasing temperature. The importance of this Curie-Weiss law is that it explains the ferromagnetic to paramagnetic transition. But if you remember in the theory of paramagnetic materials, we have seen that the susceptibility is proportional to 1 over T, which was only the Curie law. So this means that the susceptibility of paramagnetic materials is inversely proportional to temperature. But this doesn't explain the ferromagnetic to paramagnetic transitions. While the Curie-Weiss law, it explains the ferromagnetic to paramagnetic transitions also, along with the susceptibility in the paramagnetic region. These both laws are correct, but are valid in different contexts. The Curie law is correct for paramagnetic materials where there is no strong spin-spin interactions, while the Curie-Weiss law is correct for ferromagnetic materials above the Curie temperatures. So therefore, if you are dealing with a simple paramagnet, then you must use the Curie's law. But if you are dealing with a ferromagnet above its Curie temperature, then you must use the Curie and Weiss law. Now let us again plot m divided by ms as a function of y. Now let's come back again to our equation for m divided by ms, which was equal to bj of y, and where y was given by this. Now from equation 2 we can get the value of m as 1 over lambda times ykt divided by g mu bj minus b. This represents a linear equation with x-intercept and slope proportional to temperature. Also, as the saturation magnetization is given by ngj mu b, so therefore we will get the ratio of m and ms as, also we know that m by ms is equal to the Brillouin function. So therefore we will look for graphical solution of equation 1 and equation 4 as we have done in the previous video. But here the magnetic field is non-zero. Here the equation 1 represents the same Brillouin function, but equation 4 represents a linear equation with x-intercept when YKVT divided by G mu Bj is equal to B. That is when the M divided by Ms value is 0. So this gives the x-intercept as Bg mu Bj divided by KVT. So therefore the effect of adding a magnetic field is to shift to the right the straight line in the graphical solution. This results in a solution with non-zero magnetization for all temperatures, so that the phase transition is removed. Now as the slope of this equation is proportional to temperature, so we can again get the three situations, as temperature can be equal to the Curie temperature, or it can be less than the Curie temperature, or it can be greater than the Curie temperature. So the phase transition is removed. Or we can say that for the ferromagnet in a non-zero magnetic field, there is always an energetic advantage to have a non-zero magnetization, with the moments lining up along the magnetic field. The Weiss model contains no specific directions associated with the ferromagnet itself, but in real ferromagnets, that is not the case, and the effect of magnetic anisotropy associated with the materials is needed to be considered. That we will see in the upcoming lectures. For now, let us discuss the origin of molecular field, and we will derive the relation of exchange constant with the Curie temperature. When Weiss proposed his molecular field model in 1907, he was very disappointed that the constant lambda needed to be very large to agree with the larger values of Curie temperatures. And considering only dipole fields, it was not possible to account for an internal field which is of the order of 10 raised to power 3 Tesla, which is required for the Curie temperature of many elemental ferromagnets. But around 1928, Heisenberg showed that it was the exchange interactions which involves large Coulomb energy which is responsible for the large molecular field. Now let us combine these two theories to give a meaningful justification to the molecular field constant lambda. Now according to Weiss's theory, in the ferromagnets there exists the effective magnetic field which is equal to external magnetic field plus local internal magnetic field. While from the Heisenberg model, the Hamiltonian for nearest neighbor spins is given by minus 2 J exchange and then the summation over nearest neighbor of Si dot Sj. Now in mean field theory, instead of treating all spins exactly, we approximate the neighbors of spin I by their average value, so that the interaction term becomes Si dot average value of S. Therefore, equation 2 will become minus 2 J exchange summation of I from 1 to Z Si dot average value of S. Here Z represents the number of nearest neighbors. And since there are Z neighbors, this will be equal to the summation is replaced by multiplication over Z. Now in the thesis theory, we can assume that the molecular field lambda m gives rise to the interaction Hamiltonian as 2 minus G mu B Si dot B effective. This is the interaction Hamiltonian if we assume the spins are present in the effective field. And if we are saying that the Weiss theory and Heisenberg model are equivalent, then we can compare equation 4 and 5. So therefore we will get the molecular field equal to 2 times J exchange Z divided by G mu B and the average value of S. This is because of the fact that the Weiss theory and Heisenberg model are equivalent. Also, if you remember that the magnetization is given by N G mu B and the average value of S. So therefore, the molecular field can be written in terms of magnetization as, and if we compare this with lambda m, we will get the value of lambda equal to 2 J exchange Z divided by N G square mu B square. This is a very powerful equation as it relates the viscous phenomenological constant lambda to the microscopic exchange constant. Now, if you remember, the Curie temperature is related with this lambda as G mu B J plus 1 lambda ms divided by 3 kb. And if you substitute the value of lambda here, then you will get T is equal to 2 J plus 1 J exchange Z ms divided by 3 nkb G mu B, where ms is equal to ngj mu B. Using this, you can get the ratio of J exchange and kbtc equal to 3 divided by 2 j into j plus 1 times z. So if you want to know the value of J exchange for any material, then you only need to know its Curie temperature, the value of total angular momentum, and the value of number of nearest neighbors. And using this equation 8, you can get the value of J exchange. Or reversely, you can predict the value of Curie temperature. So this is it for today. And in the next video, we'll talk about antiferromagnetism. Thank you so much for watching this video.